You can see it.
Yes, sir. Yeah.
So N-bromosuccinimide, again, we had this reagent, right, for allylic and benzylic bromination, right? And so again, see, so in the first step, again in NBS, what we have to do is first, in the first step, we are going to abstract an allylic hydrogen, right? Allylic hydrogen I'm going to pick from here, right? Because bromine will prefer that radical which is resonance stabilized. And again, immediately I draw two resonating structure and I can see that I'm going to get two products, right? This is clear, huh?
Yeah, yes, sir.
Okay. Okay.
Yeah, yes, sir.
Okay. Okay. So similarly here we have to do how many products we are going to get. So again, we get this in the presence of N-bromosuccinimide. Again, we are going to generate an allylic radical, right? So because this
Yeah.
hydrogen will be abstracted here, right? Because we are going to get a 2-degree resonance stabilized free radical, right? And again, I draw it resonating structure and I see if I'm going to generate two different products or not. But in this case, I'm only going to get one product because it is symmetrical, right? So just one product, okay? Not like above here where we have two products. This is clear, all right?
Yes, sir. Clear.
And again, there, see, again, they will ask you the products, okay? So now you can see how these products will be formed, right? In the first step, what will happen? We are going to abstract the hydrogen from here. So I am going to generate this specific free radical double bond CH2 dot, and then I draw its resonating structures, right? And I will get something like this double bond
Yeah.
CH2 dot, and I can, right? So again, 1920.
So,
Uh,
but the first one will be major, right? Because it's 2 degree.
yes.
Okay, yeah, yes, sir.
So you see, actually, what happens is it's just a mixture, and yeah, it'll be like that as because the bromination is there. And again, in 21, again we are supposed to draw the resonance contributors for the following radicals. This you can draw. And in problem 22, draw the major products of the reaction of 1-methyl cyclohexene with the following reagents, disregarding stereoisomers. Okay, so 1-methyl cyclohexene, right? So this is what we have to draw, right? 1-methyl cyclohexane. So this we have to treat with NBS and this peroxide, right? Okay.
Yeah.
So I think there will be a lot of products for the in the first case because we'll have several allylic hydrogens, right? For example, this can also be abstracted, right? I can also abstract this, and I can also abstract one hydrogen from here, right? All will be resonance stabilized, right?
Yeah, yes, sir.
So first we abstract the first hydrogen, then we draw its resonating structure and draw the products from that. Then we draw it from the second. Uh, then we draw the free radical from the by abstracting the second hydrogen. Then we draw the free radical by abstracting the third hydrogen. And in every case, I'm going to draw the resonating contributors, right? And the products may be same or may not be same. So you have to check, okay, how many products are identical, and then you can see how many products are there. In the second case, we are simply going to add bromine across it, right? Br plus and Br minus, right? Simple
Yeah.
alkene reaction, yeah. In the third case, simple HBr addition, and in the fourth case, HBr and peroxide. Um, the orientation is going to switch because in the presence of HBr peroxide, Br dot will be an electrophile instead of a nucleophile like we have in the regular case, right? And for each reaction,
Instead
show
of
which stereois
peroxide, what will happen?
in HBr peroxide. What happens is that initially we get a peroxide, right? The peroxide is like this,
Yeah.
so it breaks into this,
Yeah.
and what happens is that one RO dot this reacts with HBr.
Oh, yeah, and some RH and BR. Yeah, yeah, yes, I got it.
right? So this is an electrophile, right?
Yeah.
This is an electrophile instead of being a regular nucleophile. So now this will add to the more substituted, and then okay.
So in 3 and 4, the same product will be found, right?
So in the 3 and 4, what will happen is this. In the third case, I will simply have CH3. And here what will happen? I'll have a bromine here, right?
Yeah.
But in the fourth
Okay, yeah,
case,
attached to the other one, the 3 degree. Yeah.
and in
Yes,
this
sir.
case, this will happen, right?
Yeah, got it.
Okay. So no revision was done, huh? Okay, good.
Okay, so this is peroxide one I forgot.
Okay, no. It's okay. Okay. So that is how it is. And I think, yeah, we are more or less going to be. So a bromine radical can remove an allylic hydrogen, and it can also add to a double bond, right? So Br dot can perform both of these things, right?
Yeah, yes, sir.
Right. And there's this special case of the cyclopropane, although it is an alkane, but it is so strained because the regular bond angle in sp3 hybridized carbon will be 109.5 degree, but here it will be 60 degree. So instead it behaves like this, it just undergoes addition reaction because this ring just wants to break, and X and Y just add like this. Huh? X and Y, see? Because this is right, cyclopropane. So what are the bond angles here? 60 degree, right? And the
Yeah.
ideal bond angle is 109.5 degree. Just imagine the strain, right? It's like somebody twists our arm, huh?
Yeah, yes, sir.
So it will just immediately break. So although it is a cycloalkane, it behaves like an alkene, and it just undergoes addition reaction. X and Y in the general case. So these general cases are put here. H added here, Br added here, ClCl added, HH added. Huh? Okay.
Yeah, yes, sir. Got it.
Okay. Now, again, more practice with multiple step synthesis, and this is what we are going to do. So, in the first example, the first thing, Neha, when we are going to perform synthesis is it, because since it is organic chemistry, we are always going to see that the carbon count remains same. So, in the first example, we can see that the carbons in this particular thing, 7, 8. Here are 8 carbons, and here only are 7 carbons. This carbon has been eliminated, right? So obviously this is an ether, and immediately I know that, yeah, if I treat it with HI, I am going to get this particular product, right? What I'm going to get is this, right? Protonation will occur in the first step, right?
Yeah.
And then I minus pure SN2 will attack, right? So what will happen? It will attack on this carbon atom, right? Because it is less sterically hindered. And this opens up like this. So I get an alcohol plus CH3I, right?
Yeah.
And then finally, it is a primary alcohol. And if I want to stop the oxidation at an aldehyde stage, I have to use pyridinium chlorochromate or a mild oxidizing agent like NaOCl in the acetic acid. Okay. Only then we will be able to stop the oxidation at aldehyde stage. Clear?
Yes, sir. Clear. So if we don't use it, then it'll become carboxylic acid, right? Yeah.
Yes. Right? Right?
Yes. Yeah.
Yeah. So, and then we move here. See. Now, suggest a way to prepare 1,3 cyclohexane. So alkanes only one reaction, bromination and bromination. Why I said bromination? We can also do chlorination because bromination is what is predictable, right? 1682 and 1, right? High degree of selectivity is there, right? So if
Yeah.
I simply brominate it, and in the second step I have used tertiary butoxide ion and I get an alkene, then I use an NBS peroxide, then I put it bromine at allylic position, and I again eliminate it. See, 2 eliminations, and we are done.
Okay. Yeah. Yes, sir.
Yeah.
Yeah.
See here again, we do this. We come backwards. I immediately see that, oh, this is there. Obviously, I have added bromination. So before this compound was formed, this must have been this, and then I can do bromination, anti-bromination,
Yeah.
right? And
Because
how can I
yeah.
arrive at here? I can arrive here by eliminating this. Huh?
Yeah.
And how can I arrive here from here? By
Adding HBr.
Br to H nu. This is an alkane.
Yeah, yes, sir.
Okay. Not HBr. Huh?
Yeah.
Okay. Got it?
Yeah, yes, sir. So if it was an alkene, then HBr.
Yeah. It's an
Yeah.
alkane. Yeah. Then HBr. Okay. Got it? And this is what they have done. Huh? Okay. Same thing, huh? In the forward direction. First the bromination, elimination, and then we have added the bromin. See, finally, what have they done? Design a synthesis for the target molecule from this indicator. So I know that if this CN has come, it can immediately come from what it can come from. It can come from CH2, and Br. Huh?
Yeah.
And this I get from some alkene. CH double bond CH2, right?
Yeah.
How? HBr and
Yeah.
peroxide.
Peroxide.
Okay. But how do I get this alkene? I can get it from by eliminating it from here. Huh? And how I can get this from my starting material? Just by bromination. Huh?
Yeah, Br to HMu. Yeah.
Right? See?
So in this, when we have the alkene and um, when we have the alkene, if we just add nickel and hydrogen that's in addition, will that also work?
Sorry, I did not get what?
So before we add the HBr, when we have the benzene ring and the ethene.
There's okay. This one you're talking.
Yeah, sir. So that one, if we just put nickel and H2B, if we do that addition, can we also get the alkane there?
From here I want to, if I use H2 nickel, right? You see what I'm trying to do. I'm not trying to go here, right? Our synthesis is going in this
Oh,
particular.
yeah, it's going backwards. Yeah, okay, yes, sir, got it.
Okay,
Yeah.
right? Clear?
Yes, I got it. Yeah.
Okay, and this is the forward synthesis. This is initially the double arrow. I said that they are the retro synthetic analysis. So now they are going backward. Huh? Before this, it would have been this, and before this, it should have been this, and before this, and then we finally arrived at the starting material. Huh? And this is the forward synthesis. Huh? This is the forward synthesis. We start with this, we bromination, elimination, HBr peroxide, and CN. Clear?
Yes, sir, clear.
Okay. So what we can do is, okay. For example, in the A part, right? So in the A part, I just have to arrive at an alkene. So from here, how can I arrive at alkene? I can use Br2H nu.
Yeah.
Alkane, only one reaction is there, and then I do elimination, right?
Elimination, yeah.
And tertiary butoxide, okay, plus or alcoholic KOH or whatever you want. And once this is done, I use MCPB. I get this.
Yeah.
Okay. And see, once I have gotten this, I can open this ring by using H plus H2O. It will always give me trans. Huh?
Oh, okay. Yeah, sir.
Okay. And this I can do everything CH2Br. I can reach till CH2OH, and then I use a mild oxidizing agent. Huh?
Yeah.
Okay. I'll use
to HMu, then elimination.
this Br, and then I can simply use NaOH. I don't even need to do this.
Oh, okay. Yeah, yes, sir.
And then I can use PCC or NaCl or acetic acid. Got it?
Yes, sir, got it.
Here what I can do, I can brominate it. Again, the same thing, halogenation. Okay. Then what I can do is NaOH, SN2.
Yeah.
Right. And then I can oxidize it. Huh? Secondary, this is a secondary alcohol. So I can use Na2Cr2O7, right? And I will get a
ketone, yeah.
Secondary alcohol. See, so we are done here. Okay. And we don't need all these. So I'm just going to skip, not even Chocolate is a health food. Chocolate has some properties which can trap the radicals, or it is the radicals which are responsible for aging and etc. And these catechins, they are able to trap those free radicals. Okay, so they are also phenol, so they can trap the radicals. So they are good source of antioxidants. So lots of fruits, and because they are good antioxidants, protect against cardiovascular disease, cancer, cataracts, and they are thought to slow the effect of aging. Chocolate is made of hundreds of organic compounds, including high levels of antioxidants. Wow, nice, huh?
Yeah.
Okay, so you can eat chocolate, huh?
Yeah, yeah, sir.
Okay, tell your mama. Okay, chocolate is a health food, huh? Okay. Okay, radicals and stratospherical zone, and again this is something. So how the our ozone layer is being depleted? See, first, due to the ultraviolet radiation, right? O2 breaks into O radicals, and then O plus O2 gives me ozone. Okay, this is how ozone is formed.
Oh, okay, yeah, yes, sir.
Okay, now these chlorofluorocarbons from our refrigerators and air conditioners, they are going to break homolytically like this. CCl bond is weaker, so it is going to break. And after that, this Cl dot start reacting with O3. See, this is the ozone layer, and it will deplete it because it is converting everything back into oxygen. See, back into oxygen, back into oxygen. So the O3, it is these radicals are reacting with O3, ozone layer, right? So now you can see how it is happening. In 1979, it was like this. See,
So how
and
did the last step happen?
this, see, again, you have to just break it. Just
Oh, okay, yeah.
yeah, okay, just break it. You will be able to break it simply. So see the ozone layer. Huh? It is getting depleted. Huh?
Yeah.
Yeah. See, that blue thing is increasing. Okay. Anyways, so I think, yeah, this is. So again, we are more or less done with this. Again, these are essential concepts. Okay. You can see. So alkanes are saturated hydrocarbons. So free radical substitutions. Again, relative stabilities of radicals are 3 degree, 2 degree, 1 degree. Reactivity, selectivity principles, and everything is like it's cool. Okay, whatever we have learned. Now let us look at the reactions. See, so this is the reaction. Obviously, we take the alkane in excess, right? Because that is going to increase the probability that the radicals are going to collide with the CH3 instead of CH3 CH2 Cl, right? So dihalogenation, trihalogenation, they are going to be checked. We can check them if we use the excess CH3, right? Because larger concentration means that Cl dot will only react with CH3. It will, if it starts reacting with this one also, then another chlorine will get substituted, right? So we just wanted to be monochlorination, and bromination is more selective than chlorination, right? This we know. Okay.
Yeah, yes, sir.
Okay. And this is again how the peroxide is formed. This we have. This is again. I mean, see. First, R dot is going to abstract from here, so I'm going to get ROCHR dot here, and then O2 like this. Okay. And then O dot will be here, and then that will abstract the hydrogen. So I'll get O dot. Huh? And
So
if
how is it abstracting the hydrogen?
now after that it will abstract the another hydrogen from
Oh, okay, yeah, yes, sir.
it, right? So we'll get this product. Got it?
Yeah, got it.
Yeah, we have not done this, but since I thought, okay, I'll just now HBr peroxide, the orientation gets switched because Br is an electrophile here, right? Because Br is not a Br minus, it is a Br radical, right?
Yeah.
And finally, again, bromination will occur in benzylic position, NBS with NBS allylic position, right? See, right?
Yeah, yes, sir. Got it.
Okay. So, okay, great. So let us Let's do this 26 first. Okay. I think, yeah. Do 26 and send it to me. Okay. Yeah. Do 26 and send it to me. Then we'll do more problems. Whenever there is NBS, okay, we first abstract the hydrogen, allylic hydrogen, and then we draw the resonating structure and we check if there are two products, right? This is quite a good candidate for more than one.
Sorry, sir, I didn't
This
hear.
this question is a good. We can phrase it like more than one choice correct, right? Because we'll
Yeah.
yeah.
Sir, here in the B part for all of the allylic hydrogens, and for all of them, all are coming as
This is one. This is one. They are same, right? And there is another two.
yes, sir, yeah. But for one of them, I'm getting bromine attached to 2 degree, another one 3 degree. So only the 3 degree will be major,
No, no,
right?
everything will be found in the lab. Okay, okay. But yeah,
Oh,
major you can say. Huh?
oh, okay. Yes, sir. That's that. Yes, sir. Done.
Okay, Senate.
Sir, for the E part, I had a doubt here. So, we use CH2Cl2 only when there's an alkene, right?
Yeah.
So, sir, I thought,
So I don't think so. There will be any
yeah,
product,
no
right?
reaction,
Yeah.
right?
There won't be any product form. Okay, right?
Yeah, yes, that's what I got.
Because we won't be able to generate free radicals, right?
Yeah, that's what I got.
Yep. That's correct. Enough will be able to. I think either they missed a double bond. So, yeah.
Yes, sir, sent.
Okay. Yeah. Great. Okay. So I'm going to just going to move to the next one. See. So I'm just going to tick which you have to do. See, 34, we know that free radical will be formed here, then a resonating. Oh, sorry. We can also form it down. It's the same thing, right? So here
Yeah.
and resonating and this, right?
Yeah, yes, sir.
34 you need to do, and 36 you do. All these are homework. We'll take up the next chapter. You're not sending me homework, are you? You send sometimes when I give you. Okay.
Yes, sir. Last class, I don't think there were many.
Yeah, there was no homework. So again, 39, 40, 42, 43. See, this is a cyclic ether. Huh?
Yeah.
So if I add HBr peroxide here, I'll get a bromine here. Then I do an add sodium and I generate a O minus Na, and then it intramolecular Williamson. RO minus and RBr.
So how? After the BR?
We use a sodium ion and we'll get
Oh, okay. Yeah, got it.
right. We'll generate alkoxide ion, right?
Yeah.
Okay, this is a homework. Huh? I'm not supposed to discuss this, but okay, this you have to do, and I think this is going to be enough. Yeah, this I'll discuss a bit. I think last one I'll discuss. See, so in the peroxide, after the peroxide I've broken, for this I'm talking about 49. So RO dot is going to pick a hydrogen as usual. That is its job, right?
Yeah.
And I'll get a CCl3. Yeah?
PCL3, yeah.
And CCl3 dot is going to add somewhere here. See. So I'll get this. I'll get a dot. Okay. And now I'll number them. So I'll say 1, 2, 3, 4, 5, 6, 7, 8. Okay. So I'll say 1, 2, 3, 4, 5, 6, 7, 8. So see what is going to happen. This 2 is going to attack this 6. This is a free radical. Now free radical is going to see across the intramolecular.
So why does it join across 6 and why not 5?
Because we are going to get these two nice 5-membered rings. If I add it to 5, it will be a 4-membered and 6-membered. Huh?
Oh, okay. So because the anchor will have lesser
Yeah,
strength.
yes. 5-membered rings are more
So,
stable.
but then
4-membered
we'll
has
get
more.
one 4-membered and one 6-membered. So 6-membered is highly stable, right? So why
6-membered is more
not?
stable, but 4-membered is less stable. So 2 5-members are better. And
Okay,
plus
yeah.
also, you see, they have asked that give us the mechanism for this. So they have isolated this product. But yeah, the reason is that the 2 5-membered rings are much
Okay, yeah, yes, I got it.
more. Okay. So yeah, that's it. I think we are done. So again, Neha, you can go through this, draw the curved arrows for how we have to draw for the radical reactions. We know this half,
Yeah, half arrow.
half bow, and sometimes the lone pair are shown, sometimes the lone pairs are not shown. Okay, this is sometimes the lone pair are not shown. Okay,
Yeah.
Sometimes the lone pair are not shown. So you can just go through them. I don't think so it's much of a task now. And as usual, all the answers to these curved error problems are given. Okay. So you can also check them. Here they are. Answers. Okay. So after drawing, you can check them. Got it?
Yes, I got it.
Okay. Now we enter this new. See how nice, huh? So see how nicely they have opened this chapter, huh?
Yeah.
Okay. So I'll just tell you first. So she now I'll tell you about this author, huh? Okay. So she has a parrot, okay,
Yeah.
3 dogs, 2 cats, okay, and she also bring her dogs Zeus to class, huh?
Yeah.
Okay. Zeus is also attending organic chemistry, okay. And she loves reading suspense novels, huh? That is how she has built it very nicely, huh?
Yeah.
A structured way, it's like this is happening because this is happening because this is happening, huh? See how long she waited for HBr peroxide, right?
Yeah.
She did not introduce it immediately in the alkene chapter, huh? Right?
Yes, yeah.
Like her Indian, because she has to teach radicals. Anyways, so now the carbonyl group, and see, this is the carbonyl group, right? This is what we know as a carbonyl group, right? And these are acyl groups. Okay, this you know, right?
Yeah.
So now these are the two class of carbonyl compounds which we are going to study. In the top one are carboxylic acid and its derivatives, right? These are carboxylic acid and its derivatives. In these cases, this Z atom will be more electronegative than carbon, okay? In this case, Z will be more electronegative than carbon. And in the second case of carbonyl compounds, Z is either going to be an alkyl or aryl group. Basically, this carbon will be again bonded to another carbon or a
Carbon, yeah.
hydrogen. Okay, so these are aldehyde and ketones, right?
Yes, yeah, I got it.
Right. So we are going to study carboxylic acid's derivatives first. Okay. So these are the carboxylic acid derivatives. See, in the place of Z, I have OH. It is a carboxylic acid. If I have OR dash, it is ester. If I have Cl, it is acyl chloride. In general, if I have a Br, it is acyl bromide, right? And if
Yeah.
in general, it is acyl halide. And these are amides, right? These are amides, right? See, all are amide. Successively, I'm replacing these hydrogens by alkyl group, right?
Yes, yeah, I got
So
it.
these are amides, right? So this is how the situation is. Now, let us come to this. So in the case of aldehyde and ketones, see, what is going to happen? First of all, these groups, these Z, they cannot be replaced by a nucleophile. Why? Because H minus and R minus are the strongest bases, right? H minus and R minus is this is the strongest base, right? We discussed this during the Grignard reagent, right? Because the pK of alkane is 60. Okay. RH. So it is very, 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 very weak acid. So consequently, R negative is very, 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 very strong base. In fact, it is the strongest base. So no nucleophile can come and replace this, right? Okay.
Yeah.
Now we know this rule that the weaker the base, the easier it can be replaced, right? The weaker the base, the easier it can be replaced, right? So let us look at the leaving groups here. In turn, if this leaves, I'll get Cl minus, and if I add H plus, I will get the conjugate acid, which is HCl, right? And the pK for this is -7. So HCl is an extremely strong acid. So Cl minus is extremely weak base, right? It is extremely weak base. In the case of ester, again, it will leave like this. So I'll get R dash O minus, and if I add again H plus, I will generate its conjugate acid ROH, and its pK is between 15 to 16. If this leaves, HO minus will leave. Again, I'll get H2O. Again, pK is 15.7, right? And if this leaves, I get NH2 minus. If I add H plus, I get NH3 here. And what about this? This is like really, really, I mean, this is a base, right? Ammonia is a base. It is not an acid. So why this is able to leave? Because only this can leave only when its leaving group is converted to NH3. Okay. So it can only leave when we protonated this group first by using H plus. Got it? Just like we used to protonate OH. Huh? Same thing is going on. You see, the only lollipop we can give in organic chemistry is H plus, huh? To O and N. So then the child becomes happy and we can take it anywhere we want. Huh? Okay.
Yes, yeah. So that's for all these groups or only
Don't worry, don't worry,
only
don't worry,
NH2
don't
and
worry, don't
right?
worry. We'll come to that. Don't worry, don't worry. It's just the introduction. Don't worry. Okay. Just I went. And in the case of aldehyde and ketone, we can see that now this does not have any lone pair, right? We cannot give lollipop to this, right? And convert it into a good living group. So it will never leave. So these aldehyde and ketones, these groups can never be replaced. Okay.
Yes, I got it.
Okay. Okay. Now we'll discuss these things. And she has discussed this thing. So again, this is carboxylic acid, and again you can check the naming. I think you can do it. Okay, methanoic acid, ethanoic acid, propanoic acid, and you know this, huh? Okay. Yes. No.
Yes, yeah.
You can do this, huh?
Yeah.
Okay. If you cannot do, we can run through. I can run you through this, but I think you can do. If you don't, then you can always ask me. Okay. I'll just discuss some few points which I think are important. So, see, first of all, in the systematic nomenclature, we are going to count the carbon of the carboxylic acid. But in the common nomenclature, what we are going to do, we are going to start with the alpha carbon. So this is COH, this functional group, and the next carbon we are going to call the alpha carbon, then beta carbon, then gamma carbon. Okay.
Okay. Yeah. Yes, sir.
Okay. And again, you can see the systematic name is 2-methoxybutanoic acid 1, 2, 3, 4, right? So you can immediately see, right?
Yeah.
Here it is 1, it is 2, it is 3, it is 4. So it is 2-methoxybutanoic acid. Again, I'll start from a 1, 2, 3, 4, and 5. So 3-bromopentanoic acid. Again, I start from here 1, 2, 3, 4, 5, 6. So 4-chlorohexanoic acid. Okay.
Yeah.
Okay. And carboxylic acid, in which the carboxyl group is attached to a ring, are named by adding carboxylic acid to the name of the cyclic compound. So cyclohexane and carboxylic acid. No space, huh? Between cyclohexane and carboxylic acid. And this is, we are going to call it benzene carboxylic acid. Okay. Yes.
Yes, I got it. Yeah.
Naming acyl chlorides, again ethanol chloride. Again, what we are going to do, we are going to replace this ic acid by acyl chloride. Huh? So if I have carboxylic acid, we'll replace it by carbonyl chloride. So this would have been ethanoic acid. So we are going to call it ethanoyl chloride, huh? Because we are going to replace ic acid by L chloride. This. Huh?
Oh, okay. Yeah. Yes, I got it.
Okay. Here also we would have 1, 2, 3, 4, and 5. So 3-methyl pentanoic acid. If it would have been a carboxylic acid, then we change the ic acid to L bromide, right?
Yeah. Yes, I got it.
Okay. This would have been cyclopentane carboxylic acid if this was OH, right? So cyclopentane carboxylic acid has now become cyclopentane carbo. nil chloride. So I'll just add there that for cyclic acids, so for cyclic acids, what is happening is we are replacing carboxylic acid. This carboxylic acid is getting replaced with carbonyl chloride. Okay. So cyclopentane, this would have been cyclopentane carboxylic acid. Now it is becoming cyclopentane carbonyl chloride. Okay.
Yeah, yes, sir.
Okay. Esters, an ester has an OR dash group in place of the OH group. Okay. So in naming an ester, what we do, the name of the R dash group attached to the carboxyl oxygen, that is this oxygen. Okay. This alkyl group is stated first, followed by the name of the acid. With ic acid is replaced by 8. Okay. So this thing, if it was a carboxylic acid, we should have called it ethanoic acid, but this is an ester, so we'll call it ethanoate, and we will also add this alkyl group's names initially. So alkyl group attached to this is ethyl, so this becomes ethyl ethanoate, right?
Yes, sir. Yeah, got it.
Okay. Similarly, here again, we have to cite this group first. So I'll cite it phenyl. And if I see that this acid was propanoic acid, but since it is an ester, so it is propanoate. So this becomes
Propanoid.
phenyl
Yeah, yes, sir.
propanoate. Okay.
Yeah,
Again,
got
I 1, 2, and 3 and 4. If it was just carboxylic acid, I would have called it 3-bromo-butanoic acid, but it is an ester, so I'll call it 3-bromo-butanoate. Since it is an ester, I also have to add this alkyl group initially, so this will become methyl 3-bromo-butanoate, right?
So why are we putting the methyl first? Oh, okay, it's attached to the ester. Okay, got it.
There is a rule.
Yeah, got it, got it.
Okay, no problem. Right. So, and now these are the important of it. So I'll just go through this. Okay. See, the aromas of many flowers are fruits due to esters. See, jasmine, banana, apple. See,
Oh, okay, yeah.
esters are fruity smells.
Yeah.
Got it? These are phenyl group. This is benzyl group. These are important groups. Okay. Salts of carboxylic acids are named similarly to the way esters are named. See, I'll have this color. Named similarly to the way esters are named. That is, the cation is named first, followed by the name of the acid. Again, ic acid is replaced by 8. So in the first case, cation is named first, so it is sodium. And this formic acid, it would have been, so ic acid is replaced by formic. So this becomes,
Yeah.
right? So here it is sodium methanoate, right? Again, it is 1, 2. So potassium I name first, and this ethanoic acid, so ethanoate. Again, I put sodium first and benzene carboxylic acid, so it will become benzene carboxylate, right? So sodium benzene carboxylate. And frequently the cation is omitted, so we just call it acetate, pyruvate, lactate, right? Like this. Now, this is important that cyclic esters are called lactones. Okay, I'll just let's see if looks good. Cyclic esters are called lactones. Okay, and in the systematic nomenclature, they are named as 2-oxycycloalkanones. Right. So 2-oxycycloalkanones. Oxa designates the oxygen atom. Okay. One designates the doubly bonded oxygen. Okay, one sec. See, so one designates the doubly bonded oxygen. Okay, great. So anyways, so it is going to be 2-oxacyclohexanon. Okay, 3-methyl 2-oxacyclohexanon. Okay. So basically they are just telling us that it is just a cyclohexanon, but in the second position, because this is always one, in the second position, we have a oxygen. So hence the oxa. Okay.
Yeah, sir. Yeah, I got it.
Yeah, you'll get it. So that is it. And one thing which I want to tell you is that you see cyclic ester. So obviously C double bond O, and we used to call the next carbon alpha. So alpha, beta, gamma, delta. So if I have a delta lactone, so alpha is 1, right? Beta is 2, gamma 3, delta 4. So delta lactone means how many membered ring? 4 plus 2, 6 membered ring. See, because 2 will be added because this we are not counting and oxygen we are not counting, right?
Oh, okay. Yeah, yes, sir.
See, so this is important. So here delta lactone, again delta means delta is 4 and I have to add 2. If it is a gamma lactone, gamma is 3 and I will add 2. So it is 5 membered ring. See, so this information I am getting from here. Okay, that this gamma lactone is a 5 membered ring. Again, 3 plus 2 equal to 5. I think one question in J advanced was also there, right, regarding this. So cyclic esters are called lactones and they are named like this. Okay. So again, C double bond O is given one position and the oxygen is given two. And then we go around just the usual way. So here it is 3 methyl, right? And again, 3, 1, 2, 3. Okay. So it is like this. Naming amides, again, oic acid or ic acid or yellic acid is everything is replaced by amide. So ethanoic acid become ethanamide, 4-chlorobutanamide, benzene carboxyamide because it is benzene carboxylic acid, so carboxyamide. So you have to, these are just rules and go through them and remember. Okay,
Yes, sir. Yeah.
there's nothing new here. And yeah, again, I wanted to tell you this only. That's it for the regarding the nomenclature. See, so cyclic esters are called lactones and cyclic amides, they are called lactams. Okay.
Okay. Yeah, yes, sir.
Their nomenclature is similar to lactones. Again, the same thing. I just want to tell you how. So delta lactam means delta is equal to 4 and I add 2. So 6 membered ring. Gamma equal to 3 and I add 2. Beta is 2 and 2 plus 2 is 4.
Yeah.
Again, this was very important thing in penicillin. See, we wanted to make this 4 membered ring, but this 4 membered ring will be very, very strained for several reasons. First of all, this is how penicillin works because it has this beta lactam ring. I think it was made, I think yesterday I checked, I think it was J.C. Sheehan who made it in 1957, I think. And you see, and he has to devise many new methodologies because we want to make this lactam ring and it will immediately break. Why it will immediately break? Because it will be in resonance, right? So if I draw this resonance, see what is going to happen. N is double bond. O minus, right?
Yeah, yes, sir.
So this means that this nitrogen has become sp2 hybridized. So I want 120-degree bond angle. Oh my God, from where I will bring them up?
Yeah.
So this square will no longer be a square. Okay. So that is why it is extremely reactive. None of our concern for the moment, but yeah. Yeah, I'll just take it out for the time being. We are going to come back to this. So so this was very important component for that, and this is important. So I think we are done with this. Now this is nature's sleeping pill. You know, if we have less level of melatonin, we are not able to sleep. Okay. So we want high level of melatonin because melatonin regulates the dark light clock in our brains that governs such thing as the sleep wake cycle, body temperature, and hormone production. See how important is this, right?
Yeah, yes, sir.
Okay. And this is an amide, right? And these 80-year-olds, see, if you compare the melatonin, 6-year-olds have more than 5 times the concentration than the concentration 80-year-old people. So, which is one of the reasons young people have less trouble sleeping than the older people, right? Older people, they wake up early, right?
Yeah.
They don't wake up early. They wake up early because they cannot sleep. Okay.
Yeah.
So melatonin supplements are used to treat insomnia, jet lag. Okay. When you have jet lag, whatever you are eating, whatever pill you are taking it has melatonin. Okay. So it regulates the sleep-wake cycle. Okay, clear. Now, again, we are looking at derivatives of carbonic acid. So H2CO3, it immediately breaks into two things, right? And H2O plus CO2, right? So this
Yeah,
is
got
okay.
it.
This is right. This breaks and all that. Okay. Now, these are the structure of carboxylic acid. Again, these are carboxylic acid. So obviously, carbon is sp2 hybridized. Oxygen is also sp2 hybridized. These bond angles at 120 degree, and these lone pairs. Somebody will ask in the exam, okay, in which orbitals are these lone pairs of oxygen? They are in sp2 orbital. This lone pair is also in sp2 orbital, and one sp2 orbital has been of oxygen has been used to make a double bond. See, nice picture. Oxygen is shown by this golden color, and the carbon's orbitals are shown by the purple. See?
Yeah, yes, I got it.
So this is how it is. Now we look at the resonating structures for esters, carboxylic acid, and amides. So in the case of esters, we are going to esters and carboxylic acid, we are going to get resonating structure where the positive charge will be on the oxygen. And in the case of amides, the positive charge will be on the nitrogen, right? The positive charge will be on the nitrogen. So the resonance contributor for the amide is going to be more important than these. Why? Because this is more stable, right? Nitrogen is less electronegative, so it is going to accommodate the positive charge in much better way as compared to oxygen, right?
Yeah.
Okay,
Yes,
see,
sir.
see how this suspense novel reader is building up, huh? Because
Yes, sir.
already she has done everything, and now we are just looking.
Yeah, in class always my teacher says, Amide has better resonance, Amide has better resonance, but he never tells the reason.
Okay, so this is why it is, and which is longer, the carbon oxygen single bond in carboxylic acid or the carbon oxygen bond in an alcohol? See, in an alcohol there is no resonance, right? So this carbon oxygen bond is pure single bond, right?
Yeah.
But in the carboxylic acid, if we look at this single bond, this is not pure single bond. This has partial double bond character, right?
Yeah, so it's less.
It is shorter, right?
Yeah.
Okay. Now the boiling points. See, the boiling points of amide and carboxylic acid are very, very, very greater than ester, acyl chloride, ketone, and aldehyde. Okay. We are going to discuss why. Okay. The first thing which we notice is that amide and carboxylic acid, these are the boiling points which are much higher. I'll use the green now. See, they are much higher as compared to ester. These are okay. These are here and these are on different level. Okay. So why it is like this? Let's see. So
yes, sir.
again, the boiling point depends upon the intermolecular forces. So intermolecular forces, we are going to check, right? So see what is going to happen. In the case of carboxylic acid, see, this intermolecular hydrogen bond will be formed. Oh, they will exist as a dimer. So see, effective molar mass is twice.
Yes, sir.
Liquid solution, if you have seen, I for this is half. Van't-Hoff factor. If you have not seen, forget what I said.
Yes, I've seen.
Okay, so intermolecular. So we get that obviously we know the intermolecular forces, right? Either they are van der Waals forces or dispersion forces when the molecules are non-polar, and if they are polar, then we get the dipole-dipole interaction. These are the only two types of intermolecular forces that operate, right?
Yeah, yes, sir.
And hydrogen bond is just special name given to dipole-dipole interaction because it is much stronger than a normal dipole-dipole interaction, right?
Yeah, yes, I got it.
Right. So for carboxylic acid, now we come back. Now, if you see, first we just look at the boiling points. First, I just want to see what is happening here. Alcohol is near about the same as the water, right? 100. So this alcohol is 97.4. We get that. See, carboxylic acid, it also has hydrogen bond and it will be effectively occurring as a dimer. So its boiling point has exceeded that of water. It is 118 degrees Celsius, right?
Yeah.
But look at this amide. My God, what is going on with this dude? Okay.
Yeah, because it's having a diamond. Yes, I got it.
No, hydrogen bonding is there, that we understand. But also see what is going to happen. In the case of an amide, so I'll just draw a general amide where I'm substituting the hydrogens by R1, R2, and we immediately draw its resonating structure. Here, this thing will be very, very important, right? R1, R2.
Yeah.
Because this is very stable, right? This resonating contributor is very stable, right?
Yeah, yes, sir.
So the hybrid will have a considerable this plus minus separated charges. So see, these dipole-dipole interactions will be much stronger because the plus and minus will be much larger, right?
Yeah, yes, I got it.
Yeah. See, so that is so, and obviously when these are R1 and R2 are hydrogens, R1 and R2 when they are hydrogens, we are also going to get hydrogen bonding, right? R1 equal to R2 equal to H when they are so we are going to have hydrogen bonding, and then those also from the dipole end also things are going to increase the boiling points, huh? See, and dipole interactions, they are occurring at different ends. See, not on the hydrogen end.
Oh, okay. Yeah, yes, I got
Yeah,
it.
so these are like additional, huh? Now
Yeah.
it is having hydrogen bonding also, and it will have hydrogen bond also, and these dipole interaction also. So suddenly that is why these amides have they've become double, right? Else they would have been like 118, 120 only. But suddenly amides are so much high, they're like double the water because of this reason. Okay.
Yes, I got it.
Okay. Now then we have ester, chloride, and ketone. So what is happening here? Obviously, ester will have greater boiling point because again, it's what do you call the resonance contributor for ester will be much better than acyl chloride. Why? Because in acyl chloride, Naya, what is happening? This chlorine is donating electrons, okay, and in the ester, oxygen is donating
Oxygen
the
is sitting
right.
in that.
So chlorine is giving from 3p. So this donation is not very effective because 3p orbitals are much higher in energy, okay, and carbon is in 2p orbital, okay. So this donation is not very effective. So consequently, this is not very effective. So dipole-dipole interactions in the case of esters are much stronger as compared to acyl chloride. Okay.
Yes, I got it.
In the ketone and aldehyde, there is no resonance. So ketone is higher than aldehyde because there are two alkyl groups in ketone, so they are going to donate. So okay, and so yeah, and in the case of aldehyde, what is going to happen? Yeah, the first is yeah, immediately the molar mass is going to be higher. So yeah, it is going to win from there only actually. Okay. Ketone and aldehyde, ketone is going to win just because of the R group only, right? Right?
Yeah, yes, I got it.
Right? Because the aldehyde will have a smaller hydrogen, so we'll beat it there only, right? So,
Yeah, ketone is hard. Yeah.
so these were the boiling points. Okay. Now solubility again, solubility like dissolves like if things are polar, they are going to dissolve, and if they are not, they are not going to dissolve. So carboxylic acid derivatives are soluble in solvents such as ethers, chloroalkanes, and aromatic hydrocarbons. And like alcohols and ethers, carbonyl compounds with fewer than 4 carbons are soluble in water. Okay, so that is how. And uh, Yeah. Esters and disubstituted amides and nitriles are often used as solvent because they are polar but do not have reactive OH or NH2 groups. We do not want these. Okay. So one common solvent which we looked at was dimethyl formamide. Okay. When we studied alkyl halides. Okay. And when we said that the relationship between basicity and nucleophilicity is going to get inverted only in aprotic polar solvent. Okay. Everywhere it is going to remain same.
Yes, yeah.
Now, how carboxylic acid reacts and carboxylic acid derivatives react. So obviously, I can see from here what is going to happen. This again, first word this, second word this, right?
Yeah.
First word nucleophilic because carbon has delta positive,
Oh, okay. Yeah, sir.
and we are going to expect addition because there is unsaturation, right?
Yeah.
Okay, we'll come to this. Why addition does not happen? We'll just come in a moment. So, see, the first step is fairly clear. Z minus is going to attack this sp2 carbon atom. Okay, this carbon atom is sp2.
Yeah,
And
yes, I got it.
after it has attacked, we are going to get this carbon now has become sp3. Okay.
Yeah.
And so this is called a tetrahedral intermediate for obvious reason because it is a tetrahedral. It is sp3
Yeah.
hybridized, right?
Yeah, yes, sir.
Now oxygen minus comes back and it kicks out the Y. Oh my God, because it can. Okay, why is it kicking? Because it can. Weak bases are good leaving groups. Huh?
Good leaving groups. Yeah.
Okay, so the only condition is that the Z minus should be stronger than Y minus, right? Only then it will be able to kick. If Z minus is weak, then O minus will kick Z only, right? Z minus must
Okay,
be
yeah, yes,
stronger,
sir. Yes, sir.
right? Right? Z minus incoming must be stronger. Only then it can push it, right? Okay.
Yeah.
See. So this is happening. So weaker base is eliminated from the tetrahedral intermediate. Okay, clear?
Yes, sir. Clear.
Okay. The weaker base is going to see such a small rule and so helpful, huh? Right? This rule is like it has helped in alkyl halides, right? Everywhere, right?
Yeah.
Right. So see now suppose Z minus is a weaker base. That is the incoming is a weaker base than Y minus. Then what will happen? Then it will kick Z only because
That
O
only,
minus
yeah.
is going to kick whatever is weaker,
Yeah,
right?
whatever is weaker. Yeah.
Right. And so if Y minus is a weaker base, then obviously what will happen? Y will be kicked out, right? So whichever is weaker will be kicked out. Clear?
Yes, sir. Clear.
So in this particular case, that is why nucleophilic addition does not happen because the tetrahedral intermediate is able to kick out the weaker base. Okay. So in this particular case, instead of nucleophilic addition reaction, we get a nucleophilic acyl substitution reaction. We just do not say that it is a nucleophilic substitution reaction. We call it a nucleophilic acyl substitution reaction because this is the acyl carbon and the substitution has happened at this group. Got it?
Yes, sir. Got it.
So we are going to call it a nucleophilic acyl substitution reaction because the nucleophile Z minus has replaced the substituent Y minus, which was attached to the acyl group of the reactant. All right.
Yes, sir. Got it.
Sometimes chemists also called this nucleophilic addition elimination reaction because what happened was initially this first step was addition and then this
Yeah.
second step was
Elimination.
elimination, right? Got it?
Yeah. Yes, sir. Got it.
Now, if the basicities of Y minus and Z minus are similar, then the equilibrium will be there. Sometimes Y minus will be kicked out, sometimes Z minus will be kicked out. Got it?
Yes, sir. Got it.
See? So, what we have learned here is that I think this slide, let's try this. A carboxylic acid derivatives will undergo nucleophilic substitution reaction. No, I don't like this at all. This is still better. Okay. So a carboxylic acid derivative will undergo a nucleophilic acyl substitution reaction provided that the newly added group in the tetrahedral intermediate is not a weaker base than the group attached to the acyl group in the reactant. Okay, this is too much English. I don't want it. Okay, so the incoming should be stronger than the outgoing. Got it?
Yes, I got it.
Okay, we
So,
don't want
but
that.
when it's weaker, so
Yeah.
it shows that it like Z attaches and Z only leaves. So if it's weaker, why is it attaching just like one no reaction?
Because that is the collision will always happen, right?
Oh, okay, yeah, yes, I got it. So
Okay.
intermediate will always
Yeah,
be.
it just collided and then it went back. It collided, it went back. Nothing happened. Okay. But it will obviously collide, right?
Yeah, got it.
And comparing nucleophilic acyl substitution with nucleophilic substitution, let us compare. What are we going to learn here? So when we compare these, see what is going to happen. This is an SN2 reaction, right? Okay. So this is a concerted process, right? Everything is occurring at the same time, right? Everything is happening at the same time, right? As Z minus comes, then by right, it's bond making, bond breaking is simultaneous, right? In an
Yeah.
SN2 reaction. But here, what is happening? Addition and elimination is occurring. That is all. Okay. Now the relative reactivities. Obviously, see, we compare the basicities of the leaving groups. See how we are going to compare. Here the leaving group is Cl minus, here R dash O minus, here HO minus, here NH2 minus. And then I consider HCl, ROH, H2O, and NH3. What is the order of acidity? This is the order of acidity, right?
Yeah, yes, sir.
So if this is the acid order, so Cl minus is the weakest base. They are nearly comparable. And this is the strongest base, NH2 minus. Because NH3 is the weakest acid.
Weakest acid, yeah.
So NH2 minus is a very strong base, right? And if
Yes,
it's,
I got it.
yeah, so what is going to happen? Cl minus will leave fastest. So it will react fastest. It is most reactive. Then ester and carboxylic acid, they are having similar reactivity because the pK is similar. They are both, water is 15.7 and the alcohols are between 15 and 16, right? And the NH3 pK was 36, right? So it is actually a base. So NH2 minus is extremely strong. So this is amides are least reactive. Got it?
Yes, I got it.
And here we are. So see, a weak base makes the first step easier. Why? Because it is a weak base, it does not want to share its electron well. That is why they are weak bases, right? Weak bases do not share their electrons well. Okay. So if they do not share their electron well, this resonance contributor will not be very important when it is the case of Cl, right?
Oh, okay, yeah, yes, I
Yeah,
am.
because Cl minus is a weak base and
Weak
it will
base,
not
yeah.
share its electron, it will not donate nicely. So if it will not donate nicely, this second resonance contributor will not be important, right?
Important, yeah.
Right. It means the carbonyl is not disrupted in the Cl case, right? It is intact. It is more like this. A chloride will look more like this. But esters and carboxylic acid, these resonating structure will keep on becoming more important. It means C double bond O is already disrupted. So the nucleophile will come slowly, right?
Okay, yeah, yes, I got it.
Right?
So
So
it's only for strong bases.
yeah. For strong bases, like a nitrogen will donate very
Yeah,
nicely, right? So right hand structure will be more important for amides, right?
amides, yeah.
So C double bond is already destroyed, right?
Yes,
So,
I yeah.
so nucleophile will not, I mean, it will come because the left hand structure is also the main structure in any case because it is neutral, but the considerable character for the second has increased here. So, weak base is going to make the first step easier. That is, the nucleophile is going to come faster to those compounds where Y is a chlorine, right? Acyl chloride we are talking about, right? So the first step is easier here, right? And weak base also makes the second step easier. Why? Because if it is a weak base, so it is easier to eliminate, right?
Yes, sir. Yeah.
So weak bases are going to help in either cases. So weak bases are very nice, huh? Weak base. So see what is happening here. This reaction will be going right because it is a strong base. CH3O minus is a stronger base as compared to Cl minus, right? Because
Yeah.
its conjugate acid is CHCl, CH3OH. So obviously this is strong acid, so this is weak base, right?
Yeah.
And this is strong acid. So here it is strong. So strong nucleophile is able to replace the chlorine. But if I want to convert this into an acyl chloride, and if I think this is something which I am going to get, I'm not going to get this. Why? Because Cl minus is a weak base and it cannot replace this. Because in the first step, what is going to happen? In the first step, this will open up.
Oh, okay. Yeah. Yes, I got it.
See? And OCH3 and Cl. And which will be expelled? Cl only will be expelled, right? Because it is
Yeah.
a weaker base. So see, no product, right? Oh, OCH3, right?
Yes, sir. Yeah.
So I cannot prepare a more reactive carboxylic acid derivative from a less reactive one. I cannot prepare a more reactive carboxylic acid from a less reactive one. Because in this case, what I was trying to do, I was trying to prepare an acyl chloride which is more reactive from a less reactive one, right?
Yeah.
So I cannot do that, right?
Yes, sir. Yeah, I got it.
Okay. So I can only prepare a less reactive carboxylic acid derivative from a more reactive one. Or later on, we are going to see how we can change the mechanism and then we can prepare. But yeah, if we simply want to add a nucleophile, then it will not go. And why it will not go? Because after the first step, the tetrahedral intermediate is going to expel the weaker base, right?
Yeah.
Okay. So that is how it is going to be, right? Now we are going to look at these diagrams. So see, in the first case, the incoming base is a weaker one as compared to the leaving group. So that is why the second hill which the tetrahedral intermediate has to climb. This is the second hill which the tetrahedral intermediate has to climb. See, tetrahedral intermediate, and now it has climbed an initial hill, and now it has to climb a bigger hill if we want to expel it. So this will not happen. This is a diagram where the incoming nucleophile is a weaker base than the group attached to the acyl group. Okay, the first one, just focus on the first one. Okay, so the second hill is higher. In the second case, what is happening is the incoming is what is happening? The incoming nucleophile is a stronger base. So initially, it has climbed a bigger hill. Now it is a tetrahedral intermediate, and now it is able to expel the weaker base nicely. It's a small hill now it has to. So now we are getting the product. So in this particular case, in this diagram, in the diagram B, what is happening is the incoming is stronger as compared to the outgoing. In the first case, what is happening? The incoming nucleophile is a weaker base. Okay. That is why no product is formed because the second hill is higher, which it has to climb. In the third
Yeah.
case, the nucleophile, incoming nucleophile and the leaving group, they both have the nearly like the ester and the, then we are going to get the equilibrium. See. We can revisit
Okay.
this,
Yeah. Yes, I
right?
got it.
We can also visit in the after the kinetics because anyways, she taught kinetics, but we skipped because we are already going to learn the chemical kinetics. But anyways, right? So this is how it is. Okay, you can simply see how things are going on, right? Just so it's a very nice. Now I can immediately see option A, option B, option C, and option D is none of the above, huh? So in none. So in which of the following reaction, huh? In which of the following reactions the carbonyl group, the carboxylic acid derivative will not give the product? So the answer will be A. Huh?
Yeah.
Right?
Yes, sir. Yeah, got it.
Yeah. So this is how I made this question. So I'm telling you. Okay. So this is how, and most of the people will just leave it, right? So now again we have to see that where the products, obviously we can never form acyl chlorides from anything, right? Because Cl minus is a weaker base, no reaction will occur here. Cl minus cannot replace this NH2 minus, right? Because, right?
Yeah.
So HO minus also cannot replace NH2. Only in this case the reaction will go where HO minus is the incoming nucleophile is a stronger base as
Stronger base.
compared to the
Yeah.
outgoing Cl minus, right?
Yes, sir. Yeah, got it.
Okay. Now we are going to look at reactions of acyl chlorides. Actually, we already know reaction of acyl chlorides because they are going to undergo a nucleophilic acyl substitution. Okay. So see what is going to happen. See RCOCl and the nucleophile CH3O minus. We have attached it. We have attached the nucleophile. We have attached the nucleophile. Huh? See the Z group.
Yeah, yes, sir. Got it.
Yeah, because it will be nucleophilic acyl substitution, right?
Yeah.
Okay. So now we are going to see mechanism. So for the first, we are going to see the mechanism for the reaction of an acyl chloride with a negatively charged nucleophile. When the nucleophile is negatively charged. So if it is negatively charged, then what is happening? RO minus is attacking this. This is going to open up. Tetrahedral intermediate is going to get formed. O minus is going to expel the weaker base, Cl minus, and we are going to get the ester, right?
Yeah.
This is fairly clear.
Yes, sir. Clear.
Now we are going to see the mechanism for the reaction of an acyl chloride with a neutral nucleophile. Okay, when the nucleophile is neutral. Here it was RO minus, now it is ROH. Now the nucleophile is neutral. Okay.
Okay. Yeah. Yes, sir.
So in the first step, it attacks and we get a tetrahedral intermediate. And also you can see that oxygen has acquired a positive charge because the incoming nucleophile was neutral. So I've told you whenever oxygen acquires a positive charge or a nitrogen acquires a positive charge and it has a hydrogen, it will immediately lose the proton to stabilize itself. And that is what has happened. Okay.
Okay. Yeah. So where is this B coming from?
Forget it for the meantime. Okay.
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 Yeah.
Because ROH can also pick this proton, right?
Yeah. Yes, sir. Got it.
Okay, got it. Okay. So after that, what has happened is now you see, now this tetrahedral intermediate is the same whether, see, these both tetrahedral intermediates. So whether the
Okay. Yeah.
nucleophile
The
was
same.
negatively charged or the neutral, the tetrahedral intermediate from which the weaker base is getting eliminated is the same thing. Okay,
Yeah.
got it? And
Yes, I got it.
then it is knocked out. Oh no, not with this. So yeah, this is fairly clear to us now, right?
So it's the same thing, just that one was
One
charged
additional
by
step where it
protons.
loses the proton, right?
Yeah. Yes, sir.
Okay, because it is neutral, so it will become positively charged. So only one additional step is there where it will lose the proton. Okay. Now, in the case of amide or amines, see what is going to happen. Okay. Okay. See, in the case of amines, I'm going to just put it here. So suppose I have RCOCl. So I have CH3NH2. I'm showing it using this. So the first step is this, and it opens up. I get a tetrahedral intermediate RCO minus Cl and nitrogen and H and CH3 and nitrogen as a plus, right?
Yeah.
Now CH3NH2 is also a base, right? Weak bases, amines and, right? So it will pick up this proton, right?
Oh, okay, yeah, sir.
Right? It will pick
Yeah,
it's the
yeah.
same thing, right? The nucleophile has attacked and it will lose the proton, right? So it will lose the proton and this. Now, this will act as a base. See? Now, once if this is acting as a base, what is going to happen is actually, if this picks up a proton, then see what I'm going to get is this RCO minus Cl and NHCH3. And this CH3NH2 after picking this proton has become CH3NH3 plus and Cl minus. And later on Cl minus will come. I'll just put. So now this cannot act as a nucleophile anymore, right? Because it has become CH3NH3 plus, right?
Yeah.
Okay. So that is why in the case of amines, we are using two equivalents. That is why in the case of amines, we are using two equivalents because one equivalent is getting destroyed, right?
Yeah, sir, got it.
See, that is why we are using two here. Okay.
Yes, sir, yeah, got it.
So with the ammonia and these, we will use two equivalents. So same thing here with the NH3, they have used two equivalent because one equivalent will react with the H plus and
H
it no
plus,
longer
yeah.
can function as a nucleophile, right?
Nucleophile, yeah.
Right. And again, they have asked what neutral nucleophile you can use. So for here, I will use H2O, NH3, two equivalents. Huh?
Yeah.
We have to prepare this from acetyl chloride. From this, we have to prepare. So obviously, this
Yeah,
chlorine, right?
yeah.
And we also have to use a neutral nucleophile. So here we will use this OH.
Yeah. So next one, two equivalents.
This I'll use cyclohexanol. This I'll use paranitrophenol. Clear?
Yes, sir, clear.
Okay, so you have homework also, and the in chapter exercises, whatever these I've discussed, whatever I have not discussed, you go through 13 and 14. Okay, 14 is solved, but you still go through it and do it on your own. Okay,
Yes, sir, yeah.
so from now on, these Zoom lectures, I've shifted to Zoom because I can record the lecture. I'm going to create a playlist by your name and I'll share it to you so you can watch this lecture again if you want. Okay,
Oh, okay, yeah, sir.
okay, that'll be good, I thought. Huh? Right, you can always go back and see, huh? Right?
Yeah,
Okay. Okay. See you in the next lecture. Huh?
yeah. Thank you, sir.
Okay. Bye.